In this next section, 12.1, we're going to begin studying what is called simple harmonic motion. Without a doubt, the equations that govern simple harmonic motion and simple harmonic motion itself are among the most important in all of physics and all of science. It's basically because what we're looking at is the response of a system that is near equilibrium. And a system near equilibrium either will exponentially go toward that equilibrium, like a door that's gradually closing under friction, going to its equilibrium point, or a swinging door, or a swinging pendulum, or a mass that's oscillating at the end of a spring. All of these are simple harmonic motion. And it's even a more important problem than the problems that we discussed in the first few chapters having to do with motion and a constant acceleration. Because you notice those problems of motion in a gravitational field all had a constant gravity. Therefore, the force that we looked at was mass times the acceleration due to gravity, and this was a constant at every point. And therefore, we could solve these relatively easily. Now what we're going to be looking at is not where the force is constant, but rather where the force is minus a constant times the distortion from equilibrium. And we're going to look and see what type of motion arises from this, and that motion will turn out to be what is called simple harmonic motion. So these are systems distorted from equilibrium and released, and if they're without friction, they will oscillate about that equilibrium forever. And that oscillation has a mathematical form of either a sine or a cosine function and is called simple harmonic motion. Well, let's take an example of that and show what happens. Let's take this force, and you recall that force is mass times acceleration, so we can write mass times acceleration is equal to our force, which is minus k times x. Now, what is the acceleration? The acceleration is the second derivative of x with respect to t. And I can bring this term to the left side plus k times x, and this will equal to 0. So this is our fundamental equation. This is the equation for a spring force, Hooke's law. Hooke's law, that's a force proportional to the distortion with no friction, and no applied force. In other words, we're not going to apply any other force to this other than the force of the spring. Now, what would this apply to? It might be a system where we have a mass m that hangs, and the equilibrium point here is at 0, and then we take this and pull it out or compress it up and let it go. If we have no friction and there's no other force on it, this would be the equation of the motion. This is Newton's second law. Why? It's force. Force is equal to mass times acceleration. You'll notice here that this is a differential equation. It's what is called a second order differential equation because the second derivative is the highest derivative. It is linear because x and its derivatives are all multiplied by constants. And it is homogeneous because the right-hand side does not have a constant or some other type of force. All the terms that are x or its derivatives are on the left, and the right-hand side is 0. So this is a second order linear, homogeneous, differential equation. You can say, oh gosh, I haven't had differential equations. I haven't even learned much about calculus. Well, we're going to use just a little bit of calculus to derive this solution and prove that it works. But if you're not using calculus in your course, all you have to do is remember what the solution is. And that, of course, is going to be critically important. what we're going to do is we can ask the question now, do you know of any function such that the second derivative is proportional to the function? Well, if you start thinking about things like x cubed or x to the nth, and we take its derivative, we get only x to the n minus 1. That certainly doesn't work. But if you think about the sines and the cosines, if I differentiate a cosine once, I get a sine. If I differentiate it again, I get a cosine again. So the cosine differentiated twice is proportional to a cosine, and likewise a sine is. So we're going to take a cosine function, and what we're going to do here is we're going to assume that our solution x of t is equal to some constant times a cosine of omega t plus some phase angle. This will be called the amplitude, this will be called the angular velocity, and this will be called the phase. Now, when is this going to be a solution? Well, let's take its first derivative. So dx dt is going to be equal to a. When I take the derivative of the cosine, I get minus the sine. And so that would be minus, and this is a constant. So when I take its derivative, I get nothing, but the derivative of this is going to bring out an omega sine of omega t plus delta. Now I take the derivative of this again. So the second derivative of x with respect to t squared is going to be equal to minus a. Again, when I take the sine, I'm going to get a cosine, but I'm going to bring out a factor of omega again. So I get omega squared cosine of omega t plus delta. Again, the delta is just a constant, so I get no derivative there. Derivative of the cosine is, of course, of the sine is the cosine times the derivative of the argument. The derivative of the argument would be d omega t dt, and so that just gives me a factor of omega. So now, if I plug this in, I can say, okay, so my solution must be, I must have the equation then, mass times the second derivative, which is going to be minus a omega squared cosine of omega t plus delta. That's mass times the second derivative, plus this term here, which is k times x. I can bring it to the other side and say that would be equal to minus k times x itself. Well, what is x? It's a cosine of omega t plus delta. Now, how do we check and make this sure that this is a solution? Well, we've got a cosine over here, cancels the cosine over here. We have an a over here, cancels the a over here. We have a minus sign here, cancels the minus sign here. And what we end up with is m times omega squared is equal to k. Therefore, we get m omega squared is equal to k, or omega is the square root of k over m. Very important, because what we have now proved is we have proved that this is a solution, is a solution if and only if, which is sometimes written this way, IFF, if and only if omega is given by this expression here. Let me draw an arrow over here. So if this omega is the square root of k over m, then this will be a solution to this equation here. This is the equation for a simple harmonic oscillation, homogeneous differential equation, second order, no friction. And so this is an incredibly important result. And it tells us that our solution is going to look like this. Now, what are these things like? Let's look at this in greater detail. We have a cosine of omega t plus delta. What are these various terms? Well, you recall that the cosine oscillates. So our solution is going to look like this. It's going to oscillate forever. This might be a mass on the end of a spring, and remember, there's no friction, and that's why it oscillates forever. But the cosine, you recall, has a magnitude of 1. And since the magnitude of this is 1, when I multiply by A, I get a magnitude of A. So A is called the amplitude. Because it's how large this wave or oscillation is going to be. So if I pull this down or pull it up a distance A and let it go, it's always going to go to A up here and A down here, A up here, A down here, and oscillate in between the two, and A is called the amplitude. It's how big this oscillation is because the cosine is equal to 1 at its maximum point. Well, how long does it take to go through one of these cycles? Well, it takes an amount of time, capital T, where T is equal to the period. So if I think about going through one complete oscillation, amount of time T, then what's going to happen? Well, I must have a cosine of omega times T. Cosine of omega T would equal to the cosine in that period would go through exactly an amount of 2 pi. That's one full oscillation. The delta doesn't change before and after. I still have the delta there. So if I go through from T to from 0 to capital T, one full amount of period, then in fact omega times that must give 2 pi for one full period. So remember that equation, that omega times T has to equal to 2 pi. And what that does is it tells me what omega is. Omega is 2 pi divided by the period. Or the period is 2 pi over omega. So this gives us our meaning for what omega really means. It is 2 pi divided by the period. And so if you say my oscillation is 4 seconds, then omega is going to be 2 pi divided by 4. And that tells us what omega is. Now the phase kind of is a more difficult concept. If the phase is 0, it means it starts up here. If the phase is minus 180 degrees, in other words, we started at a negative point, then it would be down here, it would be pi over 2. So we'd say delta would be equal to 0 here. It'd be pi over 2, pi, which is 180 degrees, down here. It would be 90 degrees here and 270 degrees here. And so that kind of tells us where we are in the motion. And it's possible to start this motion with some velocity. So rather than just stretching it and letting it go from the positive point, which would mean the phase was 0, like this, because I'm starting it from the positive point and letting it go, I could stretch it to the negative point, or I could start it right here, but if I just let it go, nothing would happen. I'd have to give it a velocity either in the negative direction or in the positive direction, so it would oscillate. This looks kind of messy, but you can see what the core things are. This is our core equation for simple harmonic motion. It's a linear second order differential equation with no friction. It will be a solution. This will be a solution right here. Here's our solution. If omega is equal to the square root of omega k over m. And the meaning to these terms are t is the period, then omega t is equal to 2 pi, and the amplitude is a, and this delta term is called the phase. And it's where this oscillation is in relationship to your time if t is equal to 0. Because if t is equal to 0, this term isn't there, and we have to say, what is the cosine? It's the cosine of what at time t is equal to 0? And the answer would be delta. So this gives us a pretty good discussion of this initial system, you'll notice here that the frequency is always the reciprocal of the period. Now, because of that, we can now say, well, we know what the period is. The period is 2 pi over omega. So period is equal to 2 pi divided omega. And the frequency, and this is an incredibly important equation, so don't forget it, the frequency is always the reciprocal of the period. Therefore, this implies that with this equation, that the frequency is going to be the reciprocal of this, or it's going to be omega over 2 pi. So conversely, you could say that we can say omega is the angular frequency, and this is the regular frequency, and they differ by 2 pi. Likewise, you can say omega is 2 pi times f. Now, if we have some practical problem, how do we work that, and what might we do? Well, we could take a simple system like this. We could pull it up here in a positive direction by an initial distance. Let's say x at time 0 is equal to 4 meters. And let's suppose that we already know what the spring constant is. We know that the spring constant K is going to be equal to, let's say, 8. And we also know what the mass is we're going to put on the end of this spring. And let's say the mass is equal to 2 kilograms. So now, how would we solve this problem? We will see that omega is the square root of k over m, so immediately omega is the square root of k over m. I made this easy, I know. So it's going to be the square root of 4, so omega is equal to 2. Okay, now we have an omega is equal to 2. What is our solution going to look like? Our solution is going to look like x of t is going to be equal to a, the amplitude. Well, what is the amplitude? Remember, I pulled it in the positive direction by 4 meters. So the amplitude will be 4 times the cosine of omega times t, that's 2 times t, plus the phase. Now, what is the phase? Well, you'll notice I pulled it in the positive direction and released it. So the phase is going to be exactly in phase with the cosine. So I pulled it to this point and let it go. So it'll go to the equilibrium point, to the negative point, and so forth. So this is the phase of 0 right here. So this would be plus 0, and that would be our solution. Now, having that, you can say, well, I know what omega is now. What is the frequency? What is the period? And the answer is the period, t, is going to be equal to 2 pi divided by omega. So the period is pi. Now what is our frequency? Well, if the period is equal to pi, the frequency is equal to 1 over pi. So we now have the angular frequency, the period, the amplitude, the phase, and we understand the whole solution and what it's going to look like. It's simply going to start here, oscillate forever, where its upper amplitude is going to be 4, down to a minus 4, and the period of this oscillation is going to be pi seconds. Remember the importance of this? It describes any system near equilibrium. So it describes a great deal of physics. It's also the foundation of wave phenomena, as we'll see later.